Hello, my name is Jerzy Adamski. Today I would like to share with you my vision and opinion about metabolomics and studies in large cohorts. Typical cohorts which have progressed our knowledge about how the human phenotypes are being developed in health and disease were actually mostly performed in three types of cohorts. A prospective cohort in which individuals are observed over a long period of time. In this cohort, it's quite reasonable to have a very long period of time, so decades. Some cohorts have this already. Most cohorts don't, maybe 2 to 3 years. The advantage of this cohort is that you can follow different phenotypes and the patients are own controls. Of course, the size of this cohort is rather small. In case control or disease-based cohort, a specific indication is being observed, and frequent cohorts may cover completely different indications. The advantage of use of this cohort is that the disease development and the use of different therapies could be monitored very exactly. The disadvantage is that phenotypes might cause overfitting in biomarkers because, for example, if you were studying 3 different cohorts, including that addressing the lung disease, endometriosis, and ovarian cancer, most probably these 3 different cohorts will pick up inflammatory processes as biomarkers, but these are not specific for the disease. So this is a problem if not enough phenotypes are included in case control studies. Cross-sectional studies are usually very large, they are very frequent, some even exist since decades. The disadvantage of this cohort is that they require a lot of individuals being included, some even combine it with a longitudinal perspective, but the samples are collected here not that frequently as in longitudinal cohorts. The advantage of this cohort is that the comprehensive representation of phenotypes is provided. So while you are studying a specific disease, you may as well include several other confounders and other diseases to exclude that there is an overlap and biomarkers are not specific. How to analyze these different cohorts? Well, definitely in metabolomics there are 2 different approaches, one called untargeted or non-targeted and one called targeted or quantification metabolomics. They different in the design of the study and they different in the way the people are being characterized and samples are being characterized. They have their own advantages and disadvantages. The non-targeted approach covers a lot of different pathways, might have some issues in low concentrated biomarkers or molecules from signal transduction pathways. The usual output from non-targeted metabolomics will be fold change in comparing different phenotypes, disease or health. In quantification metabolomics, low concentrated biomarkers will be covered. The other issue here is that the non-targeted metabolomics will have a large coverage but lower throughput in compared to that in targeted. However, at present it's very clear that this is in state of conversion, that we have already several well-known metabolomic approaches on the market which are covering 600 or even 1000 metabolites or even more. So the coverage is getting closer and closer, whereas the throughput is definitely the advantage of quantifying on targeted metabolomics. Now, which cohorts could be used with what type of metabolomics? For longitudinal studies and case control studies, any metabolomics would go. We are dealing in longitudinal studies with a sample set after matching VDLs ranging from 100 to maybe 3000. The original cohort might be larger, but after matching for different confounders, you will reach this amount. Any metabolomics will work here. The same is in a case control study. After matching for different confounders, you will have maybe this amount of samples being analyzed. However, if going to cross-sectional studies, the size of a cohort after matching, it will be very easily over 5,000, maybe even 100,000 and even more. By this number, we are facing completely different challenges in quality control, throughput and coverage and compatibility of the data if you are going to combine different cohorts or different studies from the same cohort even. What is the situation right now is that they have worldwide a lot of different cohorts are really big and they have huge interest in analyzing how the human health is developing, how we are aging, how is nutrition impacting our health, what is the impact of genome, what is the impact of our medication, lifestyle. They want to exchange the data. They want to make the functional assay policy applied on the cohorts. So the huge challenge is rather here how to analyze these large cohorts in a way it would bring us very fast to the level we can answer the questions. One of the examples how it could be designed is maintained by the FAIR initiative. Many information present on the web. I have extracted this just to be illustrative for the metabolomics. This holds true for all types of omics. But I will go through with these several points to illustrate what does it mean for the metabolomics applied to large cohorts. One of the key features is the key requirement for the study must be that this study is comprehensive. It means that this is covering many independent biological relevant pathways. So the coverage of metabolites and the pathway should be very, very big. The data collected must be based on the robust analytical performance of analytics. Quality control, quality assurance must be already implemented so that we are reaching a high level of reproducibility. Another key is that the study should be sustainable. It means that we are supporting integration of independent data sets. This integration should be meant for the different cohorts and different contexts, different indications. And as well that the access to the data is supported by metadata. It means as well, this is the description how the structures of data sets are actually to be understood. The accessibility of the technology must be really easy. It must be worldwide available and technically already established. Referring here rather to the availability in each laboratory and not in a single point or on a global scale. So I'm addressing here the possibility that the assays could be performed in different laboratories. Scalability is something which is of bigger interest, that once we have one assay, we have to face the story that the large number of samples must be analyzed in a cost-efficient, affordable, and a timely manner. So we are not going to spend decades, but reasonably less time, maybe years, to finish large cohorts. One option is the scalability. It means that the process of analytics could be done in different laboratories, running in different locations and countries, but working on the same cohort. I think that the ring trial is the best way to demonstrate the metabolomic suitability of a test to apply it for large cohorts. The ring trial is an idea from biomedicine which tells you what are the limits, what is the precision, how good is the assay, could it be run in different laboratories and be used for the data processing in independent laboratories to fuse them into interpretation one level. So what I'm reporting to you is ring trial of a biocrates product MXP Quant 500, which was performed recently, and many laboratories worldwide were participating, from Japan through Singapore, many laboratories in Europe, Helmholtz, MDC, Fraunhofer, University of Heidelberg, and as well biocrates. Then we had North America, the United States, Duke, Stanford, Baylor Scott and White, Indiana University, Beaumont, and as well University of Alberta. As you can see, it's a very broad spectrum of different laboratories, assigned to them letters, and they have been treated as independent entities and were processed in confidential manner. What is the ring trial design? First of all, we have international team, 14 independent laboratories, which are symbolized with this single letter assignment. Then biocrates distributed to the laboratories taking part in the assay a set of identical samples. This set included female and male human samples and as well rodent samples. For human samples, we had NIST 195 reference sample. We had as well lipemic sample, serum and plasma samples. We have pooled and individual samples. For rodents, we have mouse and rat plasma. Samples were measured in independent laboratories depicted here using the same assay, using different equipment setup, so different mass spectrometry, different LC-MS interface and different LCs. The samples were blinded, so the laboratories didn't know what they are measuring, and the quality assurance and quality control have been performed in the labs. The data were exported to Helmholtz, and the central data processing was performed by Gabi Kastenmüller and her team. So she was leading us in data processing. Now, some highlights out of this assay. We observed very high reproducibility, high sensitivity, and excellent precision. We are sure that this assay works in different hands at the same quality. What you see here is a depiction of missingness. This is missingness below LD. Different laboratories here correspond to these roads. Every single metabolite, the colors are coding. Blue is no missingness, and red is missingness at least in one laboratory. And as you can see, some laboratories differ, but this on the overall, the missingness is very low. I might say here that the clustering between the laboratories does not reflect, for example, continent. It does not reflect the vendor of the CMS equipment. The message here is very high quality of assay. Now, the comparison with certified concentration for amino acids is given here for the NIST sample. This is the concentration as reported and certified by NIST, and this is what we have measured. As you can see, there is a very, very nice correlation with values reported by the NIST. Every single symbol here represents a different laboratory. On the overall, the assay is providing the same values as that reported by NIST. Now, I would like to show you as well another overview, which is showing relative difference for each metabolites in all laboratories at the same time. So this is only a part of the picture which will follow. The relative difference between the laboratories is color coded. So red is the biggest difference, 0 is actually missingness. Green is the lowest difference. On the outer ring here you have the different metabolites. The other rings are coding for different laboratories. So this is laboratory A, this is laboratory B, and this is laboratory N. And the pie charts here are corresponding to the different chemical classes, different metabolites. Now, the whole picture shows you that actually the performance of different laboratories is very, very, very compatible. Only for metabolites which we know, like for example some triacylglycerols here, they have issues in the analytics if they are at low concentration in a given sample, the sample which was analyzed. But looking at this picture, this is a global view, and you can zoom in and compare different laboratories, different metabolites. You can easily see that the laboratories have the same performance, and if there are issues with a single metabolite somewhere here, all laboratories have the same problem. So we learned what are the advantages and what are the limits of the assay when handling it in different laboratories. Now, let us go back and look at the concept of measurement in large cohorts. The cohort size defines as well your possibility to perform any analytics, and you can imagine that in your own cohort you will analyze different types of omics, whatever, phenotyping, and many analytical assays will be implemented on the same cohort size. This is how it was done, how it will be done, nothing wrong with that. But what we are facing right now is the cohort size, which is growing. So we are growing from thousands to maybe 50,000 already being analyzed. And what is tomorrow? Can we go with the same analytics? We have to think about how to provide tools to the community at the analytical and data processing side so that we can match this problem, this challenge that the big cohorts will be analyzed as well. So I was giving you this overview of some cohorts. These are definitely not all cohorts worldwide, but at least these cohorts are talking to metabolomics, and they want to have this done very well. And I think this ring trial is providing information that using standardized assay, you can perform a lot of parallel processing, scalable, in a very large scale, using different laboratories in the same country or internationally. Now, in summary, I would like to address several other issues and advantages. We have to provide the possibility that the data which are coming from large cohorts are available in public depositories. At the same time, data ownership has to remain in hands of scientists. And this is the feature which MXP Quant 500 is providing very well. We have learned that large cohorts can be analyzed in parallel in distinct labs. We have learned that this approach supports and allows integration of different studies if different laboratories are using the same assay. Data from different cohorts, biobanks even, generated in different laboratories can be integrated into one large data set to provide the mega and global association studies. This assay is scalable worldwide and address the option for analytics in very large cohorts. I would like to thank all participating laboratories. Only PIs from the laboratories are depicted here. As you can see, there are many excellent laboratories worldwide, and biocrates was co-organizing and sponsoring this assay. I'm very thankful to biocrates for supporting this.